So let's relate to what we have in the lecture notes. So in the lecture notes, you have that circulation of some vector field that is reminded. So this is the formula that we have obtained just in the previous video. So it's going to be given by p x prime plus q y prime dt. That's one way to remember that. And some notations are going to be, so these ones, p dx plus q dy, when you haven't, that is useful when you don't have any parametric description of your curve. Okay, like we had in the previous one. So here gamma of t was given by x of t, y of t. In that case, you can rewrite it as the first here, that first one. When you don't know yet what description you can make of your curve, you're going to just use this notation, right? And so this is the line integral of the vector field v on gamma, and there is a nice notation that I haven't given you yet. This integral with a nice little circle in the middle is used to denote the curve integral, the line integral, when the curve, in the specific case, when the curve is closed. So like this. Okay, p and then p dx plus q dy. Okay, so this is what you use if this is a nice notation when gamma is a closed curve. What do we mean by a closed curve, by the way? It's just something that, well, the beginning and the end can be the same ones, right? Well, if you well, you don't have to begin and end at the same at that place, but then you can do it this way. Okay, so that is a closed curve. Next, I don't know if you remember, well, I hope you do remember that we had the first time we talked about vector fields, we talked about some specific vector fields that had some property when they were coming from a scalar potential. Okay, so this is what we called conservative vector field. So this is the case that we are going to treat now, because if your vector field is conservative, it has some nice property. Okay, so let's see what it gives us. To remind you that we say that if we've got a vector field, let's say we are in two dimensions, so v is equal to p and q. We say that it's, well, p of xy and q of xy. You remember that we say that v is conservative. That means there exists some scalar potential. Well, what is going to be called a scalar potential, but the name is just a name. Let's call that f here, f of xy, so a function from R2 with real values. So with xy gives you f of xy that belongs to R, okay, such that v is equal to the gradient of f. Okay, f is a two-variable scalar function, so f has df over dx and df over dy. Okay, so basically my vector field is conservative if p of xy, if I can find f such that p of xy is df over dx and q of xy is df over dy. Okay, you remember that? I didn't give you, or and several of you came to ask me if they could use some specific properties, but I didn't give you some specific properties that allow you to find the whether a vector field was conservative or not. I wanted you to be able to find if we could have. I wanted you to be able to find the corresponding f, or not, if it was not conservative. Okay, so previously we only knew that it were conservative if you could find f. But we also knew something else. We knew in R3, let me just remind you, we knew that if V is conservative, then the curl of v is equal to 0. Okay, and that was a single way implication, all right, not an equivalence, all right. I told you not to use the reverse equivalent, the reverse implication, because we didn't know whether it was true or not at that point. And actually we still don't know, but what we're going to see is that in some cases, and but actually we're going to work on the two-dimensional case when you are in R2, we can have the reverse implication, but we still have to check some topological property. So what would be the equivalent of that? The equivalent of that would be if V is conservative, then what do I get? So I would get something like the working on the derivative of P and Q. What would I get? If you remember Schwartz theorem. Okay, the Schwartz theorem that tells you that if your function is your scalar function of two variables, so like f, has continuous second derivative, so keep this f in mind, has continuous second derivative, then the cross derivative are equal. What do we mean by this? We mean that d2f over dx dy is equal to d2f over dy dx. Okay, whether you do first the first derivative with respect to x and then another derivative with respect to y, or in the other order, you should get the same thing, right? How can I relate it to this? If p is equal to df over dx, okay, if p is equal to df over dx, if q is equal to df over dy, what's happening if I differentiate p with respect to y and q with respect to x? Okay, what do I get? I get, if I differentiate, if p is conservative, again, only in that assumption, dp over dy is going to be d over dy of d over df over dx, so that's d2 dx of f, and dq over dx is very similarly d over dx of df over dy, so d2f dx dy. Okay, so assuming everything is as continuous as we need, these should be equal to each other. Okay, so those second order derivatives should be equal to each other from Schwartz theorem. Okay, so that this is what we should get, right? So if V is conservative in two dimensions, then we have that dp over dy is equal to dq over dx, right? But again, this is only a one-way implication. So what we would like is what's happening to the other one, to the other implication. Do we have that if those derivatives are equal, then V is conservative, right? So that's the question we want to answer now, right? For the moment, we have no ways to say whether this is true or not. Okay, so actually I can break it to you. That's a theorem which is called Poincaré theorem. We don't really have the means of showing that theorem, but what is the conclusion? The conclusion of this theorem tells you that this is true, this reverse implication, true only if V, the domain of V, is what is called a star domain. Okay, that's the topological property I was talking about. So, what is a star domain? We don't know yet. Let's see what it means. Okay, so just to sum up, we have that, let me write that on the side. Okay, let me write that here. V is conservative then dp over dy is equal to dq over dx. And if we add the assumption that the domain of V is a star domain or star-shaped, then we have also the reverse implication. So we have, in the end, we would have the equivalence. Okay, so we need to define what a star domain is. Well, we're going to do this very lightly. Don't worry, it's a topological property, and we're not going to go too much into details with that. A star domain is something, well, surprisingly, is shaped as a star, more or less. It means that there exists a point in the domain, okay, such that that can reach all of the points with a straight line. With a straight line that is completely included in the domain. Straight line included in that domain. Okay, so basically, well, there exists some point in the domain such that for all points in the domain, then the segment between those 2 points is included in the domain. That means, let's say that there exists a point U, and you will have your domain. Let's say that your domain is looking like this. So a vague evocation of a star. From this point, I can reach any points of the domain by a straight line that is completely included there. Okay? There exists a point from which I can reach any other points in the domain. So that seems a bit peculiar, but the thing is that we want to exclude things like, for instance, this kind of thing in R2 store, more precisely. So I'm in R2 and I have something, a domain, okay, where I have, for instance, excluded the 0. Okay, so my domain is included in R2 star, right? That is not a star domain, because if you can't find any point that is going to help me reach any other points of the domain. Let's say if I take something around here, I can reach anything here, 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 but anything that is directly on the other side of 0, I will never be able to reach that. Okay, so that wouldn't be a star domain. So I should exclude, well, I wouldn't be able to reach that straight line out of 0. And whatever, even if you're close to that origin, if it is excluded, I will never be able to reach things on the other side. Okay, so R2 star is not a star domain. Okay, but if I'm considering okay, R2 minus, instead of just excluding the 0, I'm going to exclude the whole half line, then this is going to be a star domain. All right, so minus, for instance, or minus, what do we mean here? I'm going to exclude not only the 0, but that whole part. Okay, then this is a star domain, because whatever the point that I'm choosing here, I can reach any points including that domain. Okay, so think that on my drawing doesn't show because my lines have some width, but if my lines didn't have width, I would be able to use a straight line to join any point on that side of the origin, on the right side of the origin, to any point on the left side, excluded the line, the negative line, okay, the negative x line, right? So that is okay. This is a star domain. Okay, and basically these are the examples that you have to keep in mind. If you have a hole in it, like R2 star, this is not going to work. Okay, that is not going to work, right? Sorry about this. So another way to sum up this property is that given a vector field, okay, so we said we want the dp, so v is p and q, and I want dp over dy and dq over dx to be equal to each other. Another way to say that is to say that if its Jacobian matrix is symmetric, then we are in a star domain, then it's conservative. So good exercise. Write the Jacobian matrix of the vector field that I've given earlier. Right? If V is given by P of xy, Q of xy. Write the Jacobian matrix. So assuming you've done that, Jacobian matrix of V is going to be dp over dx, dp over dy, dq over dx, dq over dy. Okay, I have each row of this matrix is the transpose of the gradient of each component, right? And so if I've got equality, if this matrix is symmetric, so meaning that this value is equal to that value, that just means that I've got this property that I was looking for on the derivative. Okay, so it's conservative. It means that I can find scalar potential